we don't just want things to work. We want the things behind the scenes, behind the walls, and things you don't see. We want it to all be safe. Hi, this is Stephen with Service Plus Solutions again, your local electricians. And I'm here again with David with Electrician Ed. And David is a master electrician, and we're here to talk about knob and tube wiring again. So if you didn't see our previous video, it was an introduction to knob and tube wiring. What is it? Just some of the basics. There are a couple things that we did miss on that, and we're going to just touch on those here. But in this video, we're going to get a little bit deeper and talk about the pros and cons of knob and tube wiring. So this is especially important if you have an older house, or if you know someone that has an older house. We're going to get into a little bit of the meat of what are the reasons they use this wiring? What are the reasons that we talk about replacing it, and it's an issue in the houses today? And so before we do that, do we want to talk about the splices, which we maybe should have mentioned on the last video, David?
Yeah, the splices were all done just open splices were okay with that wiring method. They didn't use boxes like we do today. And with a lot of some of the older homes with knob and tube, I found do have boxes, but a lot of them don't. So wherever you have a receptacle or a switch, in today's wiring, we would put a box there, and it could be a metal or non-metallic. But with knob and tube, they didn't do that originally. So the splices were all just out in the open. They
If you could
were
see my screen, that's what a splice looks like. So go ahead and describe it.
Okay, so the method that they used for this, it's, let's say they got to the end of their spool, they're out of conductor, they're going to join onto it or tee onto it. Let's say that you've just got two wires and you're going to join them together. So they lay them, they bared, let's say, an inch of wire on each one, and so they just were down to the copper then. And they twisted it probably like 5 times. It was supposed to be strong enough to where it wouldn't pull apart without solder. And then they were supposed to solder it. And can you imagine doing all this up there in the attic on a hot day?
Right.
And then usually they didn't necessarily have to do this, but a lot of times they'd put some kind of tar or something in there to kind of create the same amount of insulation that the rest of the conductor has. And then most of the times they would friction tape that. It's just like a cloth-backed adhesive tape that they'd wrap around it, as you can see there.
And I do have one that might help visualize what the wrapping around looks like that you mentioned.
Okay.
This was definitely added on later because I noticed they had mixed wiring methods, but you could see this is where they had twisted the wires together or wrapped around, did not solder it. And so this is where we get into some of the issues of where people alter this wiring or add on to it improperly. But this is more or less what it looks like when they twist it around, except for they would have, like David said, they would solder this connection, sometimes put some, what is that, tar stuff, and then wrap it with tape.
It's not a fun splice to have to try to take apart. You just get if you're going to work with it, you're just going to cut that out of there.
And so if we're talking pros and cons, are there any pros? What are the pros to it? Or what was the benefit that they saw to this wiring other than, I'm assuming the biggest one was the cost of installation and the cost of the materials and those types of things. But are there any other pros or any other benefits to it as far as the wiring method or the way that it works?
It did its job for what it needed to do. And remember, back then, their electrical demand in the typical home was not like it is today. So it probably was just fine for the time that they made it, but they couldn't see the future. So I guess the pros, I think it looks kind of cool. It just looks kind of neat, to have these wires. But I mean, I guess that's in the eye of the beholder.
Mhm.
They knew that it wasn't the best method because in the original code book, um, it said that if you're running circuit conductors through conduit, they all have to go into the same conduit. And that was in the original code book. So
Mhm.
they already knew that, all the principles that we know today, they realized this wasn't the best method, but they had to be separated.
The
Like I'm
two
getting
wires, when we're saying the hot,
the
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 hot and the
two,
neutral, what the people commonly call them today, they're separated, and David is saying more or less they knew that it was better for those to be next to each other, right?
yeah,
But because of the
because of the materials that they had to use for the insulation. See, they only had a rubber insulation at the time. Uh, Plastics really hadn't developed to the point of being affordable. But when they did, then they began to change that insulation, got a little bit better for a while. I think that was in the 1921 possibly. Um, so some other methods started becoming available. Um, but the insulation still wasn't all, not like today's standards. Uh, it wasn't until they got plastic um, uh, forgot the word there for a second, thermoplastic insulation like we use today,
Mhm.
that it got good. So back then they knew that they had to keep the wires separate so that they could get some air circulating around them, and that would allow the wiring to dissipate heat. And so the only pro that I can see was that it looks cool. The rest of it is all bad. They're all cons. Um,
And when he means looks cool, I think from a craftsmanship perspective, you can see that those electricians who installed that, they had very neat wires. They ran them very carefully. But I did want to touch on something when you mentioned the demand, the electrical demand is different. So what I usually use to explain to people is, you got to imagine this 120 years ago. Like they may have been using their electricity for a lamp, a radio, as we go along in history, they're not really using very much electricity, and really even their heat sources were usually gas,
mhm.
radiators and things like that. So they didn't use very much electricity, and this is important, as David's mentioning, the heat dissipation. There's when electricity is flowing through a wire, it does create heat. And that's one of the major problems with this type of wiring is we use more electricity now. So there is more electricity flowing through those wires, and it's not doing as good of a job of dissipating that heat.
Yeah. The problem with rubber as an insulation material is that when it does begin to overheat, you've probably just halved its life right there. It starts to decay a lot faster than anything else that we have today. So it cracks, and it really starts showing the effects of that heat early on. And usually when you do anything, you touch it, you move it, bend it just a little bit, you're almost guaranteed you're going to lose that insulation in chunks. It's going to fall off.
Yeah, these samples that I got, luckily, so this actually was from a large office building.
Hmm.
Um, and they didn't, probably an office building, use as much electricity. The danger that we see all the time is these homes that we go into with this knob and tube wiring. This is knob and tube wiring. It's just a piece of the wire. But the dangers we see is because of the increase of electricity now, that these are very brittle. And like David said, if you were to bend this and actually hurt it just crack
Hmm.
still, I don't know if you can hear that, but
Yeah.
it has a little cracking noise. But in the houses that we see this, use quite a bit more electricity than we used to. and it's in pretty bad shape. It'll just crack right apart.
Yeah. And you'll find a lot of differing information out there if you start to research on your own about knob and tube. Um, it's a little bit confusing, some of the information that they'll give you. One place said that when you do fuse this stuff, or that's, protect it with a breaker or a fuse, it needs to be no bigger than a 15 amp fuse. And I don't find that anywhere in the code book, that you're supposed to do that. Really, and it's not even in my opinion, I feel like it should be protected the way that they protected it back then, and you shouldn't put a bigger breaker or a bigger protective device than what they used originally, for sure, because that's the way it was designed.
Mm.
So you'd really have to look at the age of the house and what was required back then for that particular insulation. So in the 1897 code book, they said that that stuff wasn't to be protected any higher than 12 amps. It was supposed to be limited to 12 amps, Stephen. And
Wow. And so this is where my job on these videos is David has all this expertise and he's done all the research, and so I'm going to tie it as much as I can, tie it back to something that people can maybe grasp. But we've talked about on our other videos about breakers and previously, what the purpose of a breaker or fuse does. It protects that wire from overheating the insulation essentially, and causing damage to the insulation. And when he's saying that this knob and tube wiring should be protected by a 12 amp fuse, that means that this insulation really can't handle a lot of heat compared to what we have now. And not to mention, it's also based on the size of the conductor. The smaller the conductor, the less it will contain the heat. Is that more or less a good way of saying that?
true, yeah. Well, yeah, and heat is heat. I think I put that in the article. It doesn't matter if it's ambient temperature. So if you're in an attic, it's going to be a lot hotter up there. That all adds. Then the amount of current that's going through your conductor is going to create more heat. If it's a bigger conductor, it's going to be able to hold that better and not heat up as much. You don't have all that resistance to the current flow that creates heat. Um, and then in the article, I talked about that physics are against knob and tube. Do you want me to get into that yet?
I do want to touch on one more thing with the heat, because I think this is one of the biggest things that people just don't understand. Like we'll tell them, and the dots just aren't quite connected. And so when we're talking about this wiring that was designed to power small loads, small electrical loads, such as, like we said, a lamp or radio or things like that. And if you think of the 12 amps that maybe it was intended to carry, which is how much electricity is flowing, that's kind of a picture of how much heat it can handle in a way. And when we go into these houses today, these 100-plus-year-old houses that we see, and we see that people have replaced the fuses with 30 amp fuses, and we see it all the time. So we see a green 30 amp fuse. What this means, especially, I've told people, that it can handle 15 amps, and this is new information to me, that really maybe it was 12, that we're talking like this wire can have 2 to 3 times as much heat as it's intended for the insulation to contain before that fuse will blow. So this is a very, very dangerous recipe, especially, and we'll get into this too, especially when we talk about situations where it's covered in insulation.
Oh, yeah.
And so this is just a very bad recipe, and I'm hoping we're connecting enough of the dots here. This is definitely going to be our longest video, I think, of the series. But if we need to come back and dive deeply into these things, then we definitely will, because this is some of the most important stuff that we've run into.
Right.
So if you wanted to continue on with where you were going to go with that.
Okay. Yeah. the electrophysics, I guess, this used to be my strongest reason for why I didn't think it was a good method. And I still don't think it was a good method. And that was before I learned that it was a rubber insulation that they used. So regardless of the type of insulation that they use, this would still be a strong argument against keeping it or using this method. And that is the principle of induction. We already talked about how when electricity goes through a conductor, it creates heat. So it's creating its own heat, adding to all the ambient temperatures. And it needed to be out there in the air so that it could dissipate that heat, which was one reason, well, the main reason you cannot cover it up with insulation. The other principle, you may know it as Faraday's law of induction. There's also Lenz's law that kind of come together, but basically what it means is that there's a magnetic field that's created around a conductor, and the magnitude of that magnetic field when electricity passes through, it depends on how much current is going through at that moment. Now with alternating current, we're going back and forth. So you've got this expanding, in any one point, you've got an expanding and collapsing magnetic field along with the voltage, we're alternating back and forth, and the current. And that's a really neat principle because we use it all the time in transformers, solenoid valves, servo motors. There's almost everything that we use in modern wiring, except for like an incandescent light bulb and a heat strip, things like that are just purely resistive loads. Almost everything electronic, your computer, your television, your phone, has inductors in it, which means that it's using the properties of a coil of wire and to magnify the electromagnetism that's happening. And what that does when it passes another conductor, it actually excites the electrons in that nearby conductor. And it could be in a piece of tin or a piece of metal that will respond to magnets. Well, when that magnetic field goes back and forth next to a piece of metal, it's going to excite the electrons in that one, and you're going to get some inductive heating. Now, I'm just going to get into this just a little bit. With our modern wiring, we've got two conductors in this circuit that are side by side, and one has a current going that way, and the other one at the same moment has the same amount of current going the other way. Those two magnetic fields actually will cancel each other out, and you have a zero magnetic field created then. This is the way I understand it. Now, I'm not an electrical engineer, and somebody may be saying, no, that's not right. But this is the way I understand it. Okay, and the with the knob and tube wiring, the reason why this is not a good method is because these two conductors are held too far apart. In the original method, they had to be at least 3 inches apart. They're already getting outside of each. They're probably, if you keep them within 3 inches, you might have a little bit of canceling effect, but they're both still going to have some kind of magnetic field around them. The closer you get them together, the more canceled out that is.
And so I want to just explain that a little bit, is you're not talking about the actual copper of the wires touching and getting close together as far as touching each other, but you're saying the two individual wires that are individually insulated, you want them to be close because there's a magnetic field around each one of them. And if they're closer, and say we're talking about a hot and a neutral wire, then that magnetic field cancels itself out and and therefore is a situation where there's less heat. And I do want to explain this really quick too, if you can hold your thought there where you're at, is this is kind of the reason why we realized we need to do these types of videos. Because the reason that people don't understand the dangers of these things is they are kind of complicated. It is kind of a complicated topic to understand. Well, there's magnetism, and that magnetism creates heat, and people just think, well, I want my toaster to work. I want whatever it is to work, right? But we don't just want things to work. We want the things behind the scenes, behind the walls, and things you don't see. We want it to all be safe. And it's very similar to like a health situation. You don't just want to go to the doctor when it's time for surgery. You want to have some semblance of nutrition and preventative, exercise and things like that to take care of your body. And so I just wanted to touch on that because that's really the basis of why we decided to do these videos. Is we started trying to explain these concepts. We've always done that as we go in people's houses. We explain the concepts, but the more we talked about it in our team trainings and things, it's really the more in-depth things that are a little bit more confusing that are the actual reasons why this is important. And so I just wanted to touch on that.
Yeah. And I think we cover that pretty well. If there's any confusion, the reason why that's a problem. Now, 3 inches would cancel it out a little bit, but in most cases, you've got your conductors at least probably 12 inches apart. So you've got a magnetic field over here, a magnetic field over here. Now, what that will do is it will create heat anytime one of these conductors goes past another piece of metal. It could be a pipe, a duct. They're supposed to be at least an inch away from any other surface. So let's say that it was. But you've also got iron core nails in each one of those knobs. So that's actually, it's getting a little bit of that induction into that nail. Yeah,
There's
there
a
you
nail.
go.
If you can see through the knob, there's a hole, and this is how it's secured to the framing member. Is they have this nail here. Of course, it's bent from me removing it, but they would pound that in to hold it to the stud.
Good. Okay. Now, so that wire is passing fairly close to that. It's closer than an inch to that metal, and I know that metal is in that inside that ceramic. But guess what? That insulator doesn't do anything to the magnetic field. It doesn't prevent a magnetic field. That's why you can play with magnets through a tabletop or whatever. That magnetic field will pass right through that. So what I'm saying is that it's doing a little extra work that it wouldn't normally have to do. It's cutting down on your energy efficiency, because anytime you're building heat where you don't want it, you're losing efficiency. So that's one of the things that we use to measure how efficient something is. If we put our hand on a transformer and it's pretty hot, we know it's not as efficient as it could be, or as we would like it to be. And almost everything will create heat, but you realize that's a loss in efficiency.
And that's an area that's an excellent point, because that's something we don't usually touch on, because the hazards of people, and maybe we should make the next video this. So I'll hold off on that, but the hazards of people, adding on to the wiring is really the main thing that we see and talk about. But it plays into the heat, of course, like we discussed, and also it's not as energy efficient because of what David's talking about here. Are there any other cons that we can talk about if we save the later manipulation of the system by adding on to it? If we save that for later, are there other cons that we should cover here?
Well, some of the research you'll do, or that you'll find, mention that knob and tube circuits are limited to 60 amps. And I think what they mean by that is the service conductors that are coming into the older homes. It used to be 60 amps was the minimum. Nowadays, it's 100 amps is the minimum service size. but a lot of people are going even higher than that with 200 amps because we're learning from mistakes of the past that we really should prepare for the future. We can't foresee exactly what people are going to be using these same systems that we're building today for. We've got the same issue that the knob and tube installers and designers had. We can't see the future, and we don't know. So it's always good to prepare for future expansion. And so, that may be a consideration also on the demand and everything, and maybe what you decide to do with your system, the upgrades that you choose.
And so I'm seeing that we probably need to just tweak a little bit of what our next couple videos are going to be, just so we could touch on these really important things. But any other things that people should know as far as the pros and cons? We mentioned the heat, we mentioned the induction, the energy efficiency. There aren't boxes typically.
Okay. Okay. Boxes, no boxes and no grounding. Okay.
Oh, yes.
Grounding is a huge thing. And I'm sorry for forgetting that right away. But
I do want to real quick, if you can, you'll definitely be able to hold that because that's a big one that we forgot. But I do want to share this picture real quick of what we mean when we say no boxes. So you can see here, typically our electrical, if you have an outlet or a switch, there's a box inside the wall that contains the sparks, if there were to be a spark. And you don't have that with the knob and tube typically. You have the wires that go, here's a piece of lath, and then there's plaster around it. So this is where there used to be a light fixture. I do have another picture where it's a little bit better because you see the plaster goes all the way around. But the wires come straight through that lath, and then they have a little protective cloth. It's kind of a thick cloth that protects it as it goes through that. But then these wires just connect directly to the fixture. And it's not necessarily as bad as it might seem, just because of they had plaster. They had so much plaster. But there is still this factor of, if there's a spark in here, especially when you go back to here, plaster is very crumbly and you see that all the time. If there were to be a spark in this fixture, and you can imagine there's probably an older fixture here, and throughout the times people say, oh, I want a brighter light bulb, so they switch the 40-watt bulb to a 60, and they switch the 60 to 100 even. There's more and more heat in that sense going on these wires, and if there's a bad connection of some sort, there's nothing preventing it from getting into the framing members of the wall and then spreading a fire from there.
Yeah, good point there. Yeah, so a lot of times when we're going into older homes that have had knob and tube, they want to change out a light fixture, or they want to add a fan. Maybe we could talk about this on one of the other videos. What we have to do, we need to bring it up to code if we're going to change it like that. So we'll put a box in there, and sometimes that's not much fun.
Let's talk about the lack of the grounding conductor with the knob and tube wiring.
Okay.
We'll try to do a broad stroke, because that's a whole nother topic on its own that we'll dig into later. But just a broad stroke of why does that matter?
Yeah. Okay. So with knob and tube, it was just two conductors, a hot and a neutral. And this is basically just two sides of the same circuit. And in between the two, you're going to have your load. So you could even think of your load as being in series with this whole thing. So it goes out on the hot side, let's say, goes to your load. It goes through the coil or whatever it is that it's going to do. If it's a motor, it's going to cause the motor to turn. It's got some resistance to it. And then it just follow that same wire back. That's the one that we call the return or the neutral. Okay, that's connected to the other side of that load. And You only need 2 circuit conductors to make electricity happen and to work. But you have to have a path, a complete path. So it goes out and it comes back to the source that it came from. And that's why we call it a circuit, because it's like a circle. It has to leave one point and come back around to that same point. So with grounding, we are adding an extra wire that doesn't really need to be there. And we never want it to carry any current, because the only time it ever does is in an emergency situation when something went wrong. We want, instead of a load there that creates resistance, we want there to be no resistance, no impedance, and this electricity is going to take a shortcut back to the source. That creates really high current. And if it's got that shortcut through the grounding wire back there, that's what the grounding wire is for, to make that shortcut. Then we need another component in the whole system for that to matter, because otherwise we're still just going to burn things down. We got to have a fuse. We got to have something that will automatically open and stop that fault before it burns something down. And that's why we use a fuse, because it's like the weakest link in the whole system. That's the place where we want it to burn up instead of melting our conductors. So it's got to be small enough. Let's just picture taking a conductor and taking part of it, the insulation off, and trimming it down to where it's really skinny right there. Really, really skinny. So basically, this is going to melt apart before the insulation melts. Okay, that's essentially what a fuse is. And a breaker will do the same thing. It has a little different functioning. It acts because of heat. It's got a bimetallic strip in there that flexes out of the way and will open the fault. Or in the case of a short circuit, it's going to be so much current going through there that it will actually magnetically open that breaker. It has another function in it that will open it. A fuse will do the same thing either way. If it gets too warm, it'll melt apart. If it gets too high of current, it'll just melt apart. And you've just stopped something bad from really happening.
And so the way that I usually describe this to people is kind of a really simplistic example, but I think it usually gets the picture across. So if you picture that you have a metal box inside the wall for, say, a receptacle, what some people call an outlet. And as David said, you only need 2 wires for the electricity to work. So you could have the hot and the neutral wire, so a black and a white, ran to the outlet. You could plug your lamp into it and it would work. It would work just fine. That's why you see sometimes people that cut that third prong off and they plug it in. Well, it still works, right? Hopefully you don't know about that firsthand, but yeah, that does happen. And what that so the example that I usually use is, let's say whoever put that black wire onto the receptacle didn't do a great job. It's really loose. And you plug your same thing into it so many times, it moves the outlet around. Maybe you use your vacuum cleaner and you're rolling it around, it yanks the cable out. Well, if that wire were to pop off the screw and touch the metal box, there is nothing in there that is going to blow that fuse or trip that breaker. It's just going to energize that metal box. And so this is the whole point of that third wire is, if you don't have that grounding wire which connects that box back to the panel, back to the earth, then that box is energized. Now you go and plug something in. The next time you touch the little screw on your cover plate and you will be shocked. And so that extra ground wire, that third prong, which the knob and tube wiring does not have, that is to create that extra path to get back and to blow that fuse. That way someone knows, hey, there's a problem here. We need to figure out what the problem is before we turn the power back on.
Yeah. Yeah, and with the grounding, and this is a huge subject, but We try to bring everything that's metal that could possibly get energized by accident. We try to bond to that. We create an entire system in a house that everything is of the same equipotential. Um, that way, if with your third prong, you plug something in, like let's say a vacuum cleaner or something like that, and there's something inside the vacuum cleaner that's gone wrong. And rather than getting shocked as soon as it touches the metal parts that are bonded, it runs back through that path all the way back to the source, trips the breaker or blows the fuse, and you don't have electrocution happening. You don't have a fire starting.
Mm-hmm. And so I think we've touched on the main topics of what are the pros and cons of the knob and tube wiring. This video got a little long, but it's okay because we touched on some really, really important stuff here. And we'll join us again on the next video. If I haven't mentioned it yet on this one, the article that David wrote, which will be on our website by the time this is posted, it goes into a lot of these things in depth. Excellent information there as well. Join us on the next video, and we'll see you then. Thank you.
Thank you.